Okay, good afternoon, everybody. I'm going to talk about Proca clouds around rotating black holes. And this work was done in collaboration with Nuno Santos, Luiz Crespino, Carlos Herdeiro, and Eugene Radu. And it was published earlier this year on JHAP. So the standard model of particle physics can only explain up to 5% of the content of matter and energy of the universe. So the other 95% are divided between dark energy and dark matter. So there are a lot of models in the literature that try to explain this dark sector. And in particular, for the dark matter, there are some models that relate the ultralight bosonic particles to this dark matter. So, these particles would have a mass that's so small that was able to avoid being detected from the current experiments, from the experiments that have been done so far. So how can we detect such particles then? One way that we can try to do that is analyzing how these particles how they interact with black holes and what kind of phenomena appears in this case. In this sense, we can use black holes as laboratories to study beyond the standard model particles. Okay, so one thing that appears in this case, so one phenomena that appears is the superradiance. So if we had a bosonic particle around a rotating black hole, if this a bosonic field around a rotating black hole, so if this field has a frequency smaller than a critical value, then it can be amplified. Then it will be amplified by the black hole. If we impose a mirror-like condition at some fixed radius, then this field will be confined to the region close to the black hole, and will suffer multiple amplifications. In the linear case, these amplifications will pile up until this will lead to a superradiant stability. But in the case of nonlinear system, when we do a nonlinear analysis, then as the field is amplified, the angular momentum and mass of the black holes gets smaller until this condition is saturated. So for the case of massive fields, the mass of the field will play the role of the mirror so that the field cannot escape to infinity. And if the field obeys this condition, then the field won't fall into the black hole. Then there will be no flux into or out of the black hole. In this case, we will have bound states around this black hole. If we consider the backscattering of these bound states in this geometry, then we can have hairy black holes. For the linear case, usually we call this bound state clouds. And so when we consider the backscattering of these clouds on the geometry, we can have hairy black holes. This was investigated mostly for the case of the scalar field, since it's the most simple case. And also we already knew how to separate the equations for this case. But for instance, for the vector boson fields, this was not so investigated since we didn't know up to recently how to separate the equations in this case. So here we are going to talk about this Proca clouds, and we also talk a little bit about the hairy black holes with Proca hair. So in order to find these bounded solutions, we have to solve the Proca equation. In the case of rich flat spacetimes, as is the case of the Kerr black hole, the Lorentz condition will be obeyed automatically, so that we end up with this equation, which gives us 4 Klein-Gordon equations, one for each component of the for potential. So this is the for potential, this is the electromagnetic field tensor. So we didn't know how to solve this equation, how to separate this equation, and if we wanted to study the Proca field in this geometry, we had to solve the partial differential equations, which is much more time-consuming and complex. But recently, work done by Frolov and others, using the explicit and hidden symmetries of a wider variety of space-times, they were able to show that these equations are separable. So using these ansatz, where this P is the polarization tensor and this Z is an auxiliary complex function, and writing this function is in this way, we find we end up, after a lot of work, we end up with these two differential ordinary equations, where this lambda is the separation constant. Okay, so if we impose, let me just go back a little. So this frequency imposes a synchronization condition between the black hole and the cloud. And now, if we impose, in order to find the clouds, we have to impose the synchronization condition. And now we have to solve, we impose the synchronization condition in these equations, and we solve these equations to the appropriate boundary conditions in order to find the clouds. So this set of equations gives us an eigenvalue problem for lambda in A, which is basically the angular momentum of the black hole. So we can assign some guess values for lambda in A and solve this equation, and we repeat this process until we find the values for this pair for which these equations obey the boundary conditions. But we are not going to do that. So instead of that, we are going to try to simplify a little bit more this equation. Such that we don't have to solve two equations, but only one. In order to do that, we will consider this work done by Baumann and others, where they studied quasi-bound states of scalar and Proca fields around Kerr black holes. So in this case, the structure of these fields around the black holes is analogous to the structure of an electron around a proton in the hydrogen atom. So these figures from their paper, and here is an illustration of the fundamental state for the scalar case, and this is the fundamental state for the vector case, for the Proca field case. And to label these states, we are going to use these quantum numbers, which are not really quantum numbers in our case, since we are in the curved space-time. So we know, here, this n is the node number, L is the orbital angular momentum, J is the total angular momentum, and Mj is the azimuthal total angular momentum. So we know that in the Kerr geometry, the orbital and total angular momentum are not conserved, so they do not have a clear physical meaning in the curved spacetime. But we can still use these numbers to label the states that we are going to obtain. Another thing that we can do to also organize the solutions that we are and analyze the solutions that we obtain is use to use another invariance of the Kerr spacetime. So the Kerr spacetime is invariant under a parity transformation, and using this, so if we have a state that gains this term under a parity transformation, we will call this an electric mode, and if it gains this term, we will call it a magnetic mode. So Baumann and others showed that using these ansatz proposed by Frolov and others, we can find all the electric modes for the Proca field. But for the magnetic modes, they were not able to do so. But Dolan, while investigating the stabilities of the Proca fields in the Kerr spacetime, he showed that at least a subset of the magnetic modes can be recovered from these ansatz. but this is still something that is open, as much as I know, if we can retrieve all the modes from the Proca field using this the answers proposed by Frolov and others. Okay, so in the work of Baumann et al., they obtained an expression for the separation constant in terms of this alpha, where this alpha is the mass coupling, so it's the mass of the black hole multiplied by the mass of the field. But they were only able to find this expression for the case of the electric modes. For the magnetic modes, though they were not able to obtain this kind of expansion, they still obtained this expression considering the marginally bound case, considering the marginally bound limit. So we can still obtain an analytic expression for the separation constant. And using these two expressions, this will be enough for us to compute the existence lines, so to compute the clouds that we, at least for the case that we are going to consider here. So we are using to consider this separation, these values for the separation constants, these expressions. They also obtain an expression for the frequency of this quasi-bound state. So if we, so this is in their case, the frequency has a real and an imaginary part. So this is only the real part. But if we consider that the imaginary part is equal to 0 and consider that the real part obeys the synchronization condition, we are able to find an expression for the mass coupling in terms of the angular velocity of. So this gives an expression for us this gives us values for which we will have an existent line. So gives us values for which we will have a cloud, a Proca cloud. Okay, so we are going to compare this analytic solution with our numerical solution. So now we only have to solve the radial equations now that we have expressions for the separation constant. In order to find the boundary condition at the horizon, we consider this expansion. We substitute this expansion in the radial equation and solve it order by order in order to find these coefficients. Okay, so here, so doing that, we find this. We have these conditions, boundary conditions at the horizon. Now we choose a guess, initial guess value for the value of A for the parameter A of the black hole, and we substitute this in the radial equation, and we solve this equation from the horizon to infinity until we find a value of A for which this condition at infinity is obeyed. So when we do that, we find these existence lines for the Proca clouds in the parameter space of the black hole. So this black line is the line for which we have extremal black holes. So we can only have Kerr black holes in the region below this curve, so in this green shaded region. And each these solid lines, this solid curve correspond to the numerical existence lines, and these dashed curves correspond to the analytical existence lines. So for small values of the mass coupling, this the numerical and the analytical existence lines coincide, but for when J is larger than L, so when the total angular momentum is larger than the orbital angular momentum, we see that as we increase the value of the mass coupling, these lines separate. For the case when the orbital angular momentum is larger than the total angular momentum, then these lines, they overlap for almost the full range of the parameters. So in this left plot, we compare existence lines for different values of the orbital angular momentum. And in this right plot, we compare existence lines for different number of nodes. And we see that as we increase either N or L, these resistance lines go more to the right, so they are tilted to the right. So this happens because in this case, these solutions, so with larger N or L, they correspond to excited states, so that we need to increase the value of the angular momentum in order to keep these clouds. Okay, here these three black dots, we are going to compute the radial solution for each of them. And this is the plot of the radial solution for those points. So we see that this radial profile is finite for all the range of the radial coordinate. And as we go to infinity, this function goes to 0. And we also want to know how these clouds distribute around the black hole. So how far are they from the horizon? So in order to do that, we plot this radius c, which corresponds to the value for which this function has a maximum. Okay, so we see that as the angular momentum of the black hole goes to 0, this RC goes to infinity. That means that as we go to smaller angular moments of the black hole, the cloud gets further and further away from the black hole. So this is consistent with the fact that we do not have this kind of clouds around Schwarzschild black holes. So Schwarzschild black holes cannot support these kinds of solutions. As we increase the value of the angular momentum of the black hole, the solution gets closer and closer to the black hole. So Hott suggested that the circular new geodesic imposes a limit for how close for the position of the cloud around the black hole. So for the case of the scalar field, we are able to analyze a bit better this region and show that the scalar cloud obeys this condition. But for the case of the Proca field, it's more complicated because as we increase the value of the angular momentum, the solution becomes more difficult to find, more challenging numerically. So we did not investigate this in this paper. Okay, here we compare the hairy black holes solutions. So these blue shaded areas correspond to the domain of existence of these hairy black holes, and we see that these domains, they are bounded by this curve. So by this red curve and by this blue curve. So these red curves, they correspond to the solitonic solution. So in here for the Proca stars, and in here for the scalar star. And this blue dashed lines correspond to the existence line of the cloud. So this one corresponds to the existence line for 0011, and this for 1011. And what we can see in here from this plot also, okay, so before I talk about that. So the case for n equal 1 was first obtained by Herdeiro and others in 2016. And in order to obtain this domain of existence, they consider points that were close to the solitonic solution for n equal 1, which they took from this paper by Brito and others. At the time, there was no evidence that we could have n equals 0 solutions for the Proca case. Okay. So we see here that n equals the fundamental case. It can happen for a wider range of the angular velocity of the black hole or of the frequency. And okay, and this happens because the minimum value for the n equal 1 case corresponds to, since this is an excited state, it corresponds to a larger lower limit for the angular velocity. So the same analysis that we did for the existence lines, we can also apply here. Here we consider the domain of the Proca field with the Proca the hairy black holes with Proca hair, with the case of the hairy black hole with scalar hair. And here we also have the same behavior. So the Proca solution happens for a wider range of this angular velocity. And this happens because the superradiant stability is stronger for the Proca case than for the scalar case. Another thing that we see in this plot is that for the scalar case, we are able to compute the solitonic solution for more backbands. But for the Proca case, we can only compute this for one backband, for only a small part. And this happens because so this black line corresponds to the extremal black hole case, and so we see that the red line in this case is very close to this black line. So this solution corresponds to very compact Proca stars, which makes them difficult to compute numerically. So in order to analyze that, we can also plot this ratio between these radius. So these are 99 corresponds to a radius which contains 99% of the mass of the star. So in the case of a boson star, we don't have a surface, but we have a discontinuity of the energy density. So the star can extend to infinity. So we have to consider this kind of radius. And when we compare this to the Schwarzschild radius, we see that for the fundamental case for the Proca field, this solution, this line comes very close to the Schwarzschild radius. So the radius of this Proca star, this Proca stars comes very very close to the Schwarzschild radius. So it's very compact. And these black squares, they correspond to the point where we have for the first time a Negro region in that solution. Okay, so here we plot the energy density surface, the constant energy density surface in this first line for the solitonic solutions, and in the second line we plot the solution for the same thing, but for the hairy black holes, the corresponding hairy black holes. So for the scalar case, we see that we have this toroidal shape for the scalar, for the solitonic solution. For the Proca, for n equals 0, so for the fundamental state for the Proca field, we have this spherical morphology, and for the Proca case with n equal 1, we have this Saturn-like morphology. And for the corresponding hairy black hole, so we have basically the solitonic solution, which is deformed by the presence of the heavens horizon. Okay, so we saw that the cloud's energy is mainly determined by the node number and the orbital angular moment, such that for when we increase n or l, we go to excited states, which correspond to larger values of the angular velocity. The fundamental hairy black holes bifurcate from the existence line of the bound state in the same way as the scalar case. The total angular momentum J allows for the existence of the L equals 0 bound state. So this is different from the scalar case. So, from the scalar case, the fundamental state happens for L equal 1. And this can be related to the morphology of the Proca, of the solitonic solutions, and also to the hairy solutions. So, okay, so recently there has been some investigation of the dynamical evolution of this kind of solitonic solutions, and they found that for the scalar case, we have a non-axisymmetric instability, and this could be related to this toroidal shape of the star. And we don't have this kind of instability for the fundamental case of the Proca star. Okay, so one thing that we can do now is try to investigate the dynamical evolution of the system. So we already have some of this type of evolution for the scalar case, and we can try to extend that to other bosonic fields, which is the case of the vector boson. And we can also try to obtain astrophysical observables. So we already know that, so if these fields, or this, if we consider these hairy black hole solutions, then we can see if this can give something that we can use to probe the presence of such fields. So if we, for instance, if these fields affect the shadow of these black holes or the emission of gravitational waves, then we can try to use these observables to probe these fields and these ultralight particles. Okay, thank you.
Okay, thank you so much, Carolina. So let's see, there is a hand here. Renana going to say something.
Can you hear me?
Yes.
Yes.
Congratulations, Carolina. Was a nice talk. Was there any attempt by you to analytically calculate Proca clouds in extreme case, just as Hod did for the massive scalar field?
In what case? In the extremo?
The Proca cloud in extreme Kerr case.
Yeah, we tried to look into that, but it was still too complicated.
I see.
Yeah,
Thank
so
you.
the equations in this case are very, very complicated.
Okay, let me see the chat. Everyone. Okay, everyone coupling. Okay, so I had some doubts, and then I can ask questions after I understand the point. Can you show your last but one slide, the one with the nice pictures of the slices of scalar configurations and vector configurations?
This one?
That one. Yes, that one.
Okay.
So here you are showing black holes, Hairy black holes. So you have solutions with a black hole and a scalar cloud, right? Is that what you mean by Hairy black holes?
Yes. Yes. So in this case, we have a black hole with a scalar cloud, and this is for the Proca, so a vector cloud.
Yeah, so there is a big difference between the scalar and the vector, right? Because the vector in the ground state, the cloud can be spherical or more or less oblate, while for the scalar it is toroidal, right?
Mm-hmm.
Okay, and how much mass can you concentrate on those clouds? Are they small compared to the black hole?
So
Are they perturbations like that? Because you are considering a scalar hair.
yeah, so the solutions can be from any part of these shaded regions, right? But
the red lines represent Proca stars, right? Or scalar
yes.
stars. But when you have black holes, then the cloud, how heavy can it be? How much mass can you concentrate in the cloud?
Yeah, so for any point, so in principle, you can concentrate as much as you want, as long as it is inside this region. So for instance, for the n = 1, you can concentrate more mass in the cloud.
Yeah, but that's a Proca star, or only the vector field, or also forming a black hole with a cloud. So I think that I have maybe I'm confused, because I think that you are talking about in one case self-gravitating scalar, okay, or a vector, and on the other hand a black hole with a cloud that can be a scalar or vector, right? Yes. Okay, so the red lines were determining the bounds of the mass of the stars, right? Not of the clouds in the black hole case.
Yeah, so the red lines, they correspond to the Proca stars in this case. And it also gives us a bound for this
for the cloud.
For this region, yes, for the hairy black holes.
Okay, okay. So the clouds are inside the red curves. Okay, that's the region
Yes,
allowed.
they are. Yes, they are between the red lines and the blue lines, which correspond for the existence lines.
Okay, and the way you get the red lines is by solving consistently the geometry and the field, right? The scalar or the
Yes.
vector.
Yeah. So when if we
for
sorry.
the clouds, you impose a black hole geometry, a background geometry, right?
Yes.
Okay.
So if we take a point that's marked 1 in here, so we are taking a point where most of the mass of the system is in of the hairy black hole is inside the horizon. But if we take a point here that's closer to this red line, then most of the mass is in the cloud.
In the cloud. Okay, okay, okay. So the cloud can be even more massive than the black hole. So you can have more mass in the cloud than in the black hole.
Yes.
Okay, okay. Very good. And is there any simple argument to justify why the ground state with n equal to 0 for a scalar and vector are so different? Why the scalar in the next slide? Why the scalar cloud is toroidal for n equal to 0, while for the vector it is spherical or oblate? Is there any simple reason to understand that?
Yes, this is related. So this is this is an illustration of what would be the fundamental state for the scalar case. So for the scalar case, we can only have clouds when the orbital angular momentum is equal to 1. Okay, so this is a condition for us to have clouds in the scalar case. But for the vector case, since now we have the total angular momentum, then now we can have clouds even for the case for L equal to 0. So in this case, the fundamental cloud happens for L equals 0. So for a cloud which does not have angular momentum, because we still have the contribution from the spin of the vector.
The spin in black hole, right? And with Schwarzschild, the cloud would go to infinity.
Yes.
Okay, okay. Very good. So thank you so much. Now I think I'm understanding this better. So any question here? No? Anybody wants to ask anything else? No? So then, well, thank you again for your talk and for your answers and for joining us. Okay, it's been very nice to have you here too.